Now we're going to talk about integration of trig inverse functions. Okay. Let's try this one. Suppose you want to integrate from 0 to 1 over 6 dx over 1 minus 9x squared square root. Now, what you should notice is the bottom underneath the square root sign is the difference of squares. It's 1 squared minus 3x squared. And what you're going to do is you're going to make this the side of a triangle, of a right triangle, one of the legs. 1 minus 3x squared. The positive part that's being squared goes on the hypotenuse, and the minus part that's being squared, namely this 3x, that goes on one of the legs. And to convince you this works, if you square this, you get 1 minus 3x squared, plus if you square that, you get 3x squared, and this is supposed to equal to 1 squared. Well, if you take away 3x squared and you add it back, it cancels out. So certainly 1 equals 1. Okay, call the angle U. And you want to find a division of 2 of the simpler sides. How about 3x over 1, which is the sine? Let the sine of U equal to 3x over 1, which is 3x. That is the substitution we're going to make. So since we need to know what dx is, I'm going to take the differential of both sides. The sine of U, the derivative of the sine of U, or the differential of sine of U, is cosine of U du. And the differential is 3x is 3 dx. So if I only had the 3, I can call it dx. I can call all of this du. But to put a 3 in, I have to bring out a 1/3. Now this integral is, well, we have the 1/3 in the front. We have this piece we're calling du, and the bottom is the square root of 1 minus, this is u. Excuse me, that's sine of u. 3x is sine of u. And it's being squared. What you need to remember is that that is cosine squared of u. That is cosine squared of u. And the square root of that is just going to be cosine of u. So this is 1/3 the integral of du over cosine of u. And of course I do have one mistake. 3 dx was not du. Because it doesn't say that. It says 3 dx equals, but it doesn't say du. It says what it says. It says cosine u du. Okay, so the numerator should be cosine u du. Cosine u du. Cosine u du. Cosine u du. And the cosine u's cancel out. So all we have is 1/3 the integral of du. But the integral of du is just u. Now, here's where the trig inverse comes in. If I interchange u and sine u and 3x, u and 3x, I can say u equals the sine is 3x. But if I interchange the u and the 3x, if this is inverse, we don't have inverse. If it doesn't say inverse and we interchange, well, now it does. So this is 1/3 times u, which is the sine inverse of 3x. Evaluated from, going back to the very beginning, evaluated from 0 to 1/6. Evaluated from 0 to 1/6. I will finish that up here, please. The 1/3 I will factor out. It's the sine inverse of 3 times 1/6, which is a half, minus the sine inverse of, well, x is now 0. 3 times 0 is 0. The sine inverse of a half. What is this angle if the sine is a half? Well, it's 30 degrees. It's pi/6. 180 divided by 6 minus, and when is the sine graph 0? The sine graph is 0 right at 0. So the answer is pi/18. Because this is just pi/6. 1 times pi is pi. 3 times 6 is 18. Pi/18 is the final answer. Let's try the next one. Suppose you have the integral from 0 to square root of 3/2 of dx over 1 plus 4x squared. Whenever the bottom, whether it has a square root or not, whenever the bottom, usually whenever the bottom is one thing squared plus or minus something else squared, or if you can get it to be like that, it's going to be what I like to call a trig substitution. I would call that u. Well, actually, let's pause on that. Let's not do that. But let us make up the triangle. 1 is being squared, that goes here. 2x is being squared, that goes there. And if both things are positive, that's what goes on the hypotenuse. 1 squared is 1 plus 2x squared. 1 squared is 1 plus 2x squared is 4x squared. And yes, that does equal the hypotenuse square. It really does. Okay, so we have a nice triangle. And if I call this angle right here u, I want to divide the two simplest sides. I want to divide the opposite over the adjacent. The tangent of u is 2x, which tells me differentiating both sides, or taking a differential of both sides, secant squared u times du. Just don't say over dx. This is equal to 2, but do say the dx here. Alright, so what we have is, if we only had the 2 on the top, I can call this not du, but secant squared u du. But to put a 2 on the top, I have to put her 1/2 on the bottom. have the 1/2. The top is just secant squared u du, and the bottom is 1 plus, well, 2x is tangent u. So that's tangent u squared. 1 plus tangent squared u. Now, what you have to remember is this identity. If sine squared x plus cosine squared x is equal to 1, well, I'm going to divide everything by cosine squared x. Sine x over cosine x is tangent x, but both the sine and the cosines are being squared. It's tangent squared x. And this, of course, is 1. And 1 over cosine is secant. But it's not 1 over cosine x. It's 1 over cosine squared x. So we get secant squared x. That is, this is secant squared x. Follow me. If I just call it angle u, tangent squared u plus 1, which is right here, that's really secant squared u. So I have 1/2. The top is secant squared u du. The bottom happens to also be secant squared u. Well, that's going to cancel. Okay, you must know this identity. Because the record, if you took sine squared plus cosine squared equal 1, and this time you divided by sine squared, well, this is 1. Cosine over sine is cotangent, but it's being squared. And 1 over sine is cosecant. In this case, cosecant squared u. You should know those two identities, or be able to derive them. I never remember them. Never. I just derived it whenever I need it. Okay. So what's left in this integral is just du and the 1/2 in front. The integral of 1/2 du, well, is 1/2. The integral of du is just u. Okay. This here tells me how to find u. Just interchange u and 2x. 2x, that's the tangent inverse of 2x. Well, that's u. This is equal to 1/2 the tangent inverse of 2x. From 0 to square root of 3 over 2. Okay, the 1/2, factor it out. Don't let it get in the way. So we have 1/2. First I plug in the upper limit. The octant of 2 times x, which is square root of 3 over 2, minus the octant of 2 times the lower limit, which is 0. Of course, the 2's cancel out. So we want to know what is the tan inverse of square root of 3. What is the angle? The tangent of what angle gives us square root of 3? Well, since square root of 3 is positive, we're in quadrant 1. Just remember, square root of 3 is square root of 3 over 1. Opposite of theta over is adjacent. Oh, I know that one. That's 60 degrees. That's 180 divided by 3. Okay, so we have 1/2 times the pi over 3. This here, octant of square root of 3, or tan inverse of square root of 3, is pi over 3. Now, of course, this is 0. So we want to know, what is the tan inverse of 0? That is the tangent of what angle gives you 0. Well, remember, tangent is sine over cosine. If sine of an angle over cosine of an angle is 0, it's because the sine is 0. The numerator is 0, which happens at 0 degrees. which is 0 radians as well. This is pi over 6, because what's in here is pi over 3. You need to be an expert at taking away 0. 1 times pi is pi. The bottoms, 2 times 3 is 6. The answer to this problem is pi over 6. Trig substitutions. We have the integral of dx over 4 plus x minus 1 squared. No, I don't like x minus 1 being squared. Well, okay, let's live with it. So remember, this is 2 squared plus something else squared. That screams in the bottom. That screams trig substitution. I'm going to call this x minus 1. I'm going to call this 2. 2 squared plus this squared. Well, that's exactly what the bottom is. That's going to equal the square root of 4 plus x minus 1 squared. This squared is 4 plus this squared is x minus 1 squared. And this does equal to that squared, which will be 4 plus x minus 1 squared. Okay, call this angle U. Find the simplest sides. The one that has the square root is not simple, and the one that just has a number is simple. So if it's not this one, it's these two. Those are simple. Opposite over adjacent. That's the tangent. The tangent of U is x minus 1 over 2. I'll bring the 2 up there. The differential of both sides, 2 secant squared u du. Very similar to the derivative, except we do not put the dx on the bottom. We put it on the other side. The differential of x minus 1 is just 1 dx. Well, that's exactly what I have on top, dx. So I can call it 2 secant squared u du. And the bottom is 4 plus, well, the bottom is 4 plus x minus 1 squared. But this is how I'm writing x minus 1. It tells me by the equal sign. But I have to square it. Well, you square 2, you get 4, and you square the tangent of u, you get the tan inverse. Tan squared u. Now, I'm going to factor out the 2 on the top. Now I'm going to factor out the 4 on the bottom. And I'm going to get 1 plus tangent squared u. And I forgot to write the du on top. What you need to remember is what I just crossed out is secant squared u. Sine squared plus cosine squared is 1. Divide by cosine squared. This is tangent squared plus, that's 1. And 1 over cosine squared is secant squared. Okay, so those cancel out. Secant squared on the bottom, secant squared on the top. And what we're left with, well, that's a half. And all we're left with is du. Well, the integral of du is u. Okay. Now, let's just clean this up a little bit. Unfortunately, part of that got erased. Tangent to tangent u is x minus 1. This time, I want to put the 2 on the bottom. And now, I interchange those. The tangent inverse of x minus 1 over 2, that's u. Okay? So I have 1/2 of u. That's how I write u. The tangent inverse of x minus 1 over 2. And there's the answer. Plus c. Plus c. Trig substitution. These are a bit difficult, so we'll do a number of them. Here's a similar one. Suppose you have dx over 1, unlike the last one, not plus, but minus x minus 1 squared. Yeah, in the bottom you have one thing squared, or you can think of it as one thing being squared. You can think of it as 1 squared. And this is minus something else squared. The positive part that's being squared, the one that has the understood plus in front, it goes on the hypotenuse. The other part that's being squared, that goes on one of the legs. Say x minus 1. And the square root goes right here. The square root of that whole thing. After all, if you square this, you get 1 minus x minus 1 squared. Plus, if you add on that squared, well, this cancels out. And yes, you do get the hypotenuse squared. 1 does equal 1 squared. Well, let us call that u. And we want to divide the two simpler sides. This over that. That's the sign. We're going to say that the sign of u is x minus 1. Take differential of both sides. The derivative or sign of u is the cosine of u times du dx. For differential, just don't put dx in the bottom. The derivative of the right side is just 1. Do put the dx on the right side. Don't put it in the bottom, put it on the other side. Okay, so instead of dx, here's my conversions. Instead of dx, I get to write cosine u du. And in the bottom, I have 1 minus, I have the 1, I have the minus, and then I have this, x minus 1 squared. But x minus 1 is sine u. That's like writing x minus 1. Then I square it. Well, remember, sine squared plus cosine squared is 1. Bring this to the other side. You have cosine squared, 1 minus sine squared. That is, that bottom is cosine squared u. Kill off one cosine on the top and one of the two cosines in the bottom. You kill off one of the two in the bottom, you're left with one in the bottom. So now we have the integral of du over cosine u. Bring in the cosine u to the top. It becomes secant u. But we know that integral. That integral is ln of secant u plus tangent u. Plus a constant, of course. Okay, but now we shouldn't have u's. So let's get rid of this. And let's just deal with the triangle. let's just deal with the triangle. This is equal to ln of secant of u. Secant of u is hypotenuse over adjacent. Hypotenuse is 1. Here's the adjacent. We get 1 over the square root of 1 minus x minus 1 squared. Plus the tangent of u. Tangent of u is this over that. X minus 1 over the square root of this mess. Plus c. But we can clean this up a little bit. Let's clean up what's inside the absolute values. Since the denominators are the same and we're adding them, we keep the same denominator. And we add the numerators. 1 plus x minus 1 is just x, plus the arbitrary constant. There's a nice way of writing the answer. Okay, that finishes that problem. The minus was a big difference. Last time we just integrated du. This time we had to integrate secant u du. Tan inverse of x dx over 1 plus x squared. Now, you can try what I said. You can put, we'll call the angle u. Since everything is positive in the bottom, the whole thing goes on the square root sign, on the hypotenuse with a square root sign. And you can put the 1 squared or the 1 and the x. 1 squared plus x squared. Yeah, that does equal that squared. The simpler sides are x over 1. That is, the tangent of u is x over 1. Okay. The bottom, the differential is secant squared u du. Well, that's dx. So dx is secant squared u du. And the bottom, 1 plus x squared, well, here's 1 plus. That's another way of writing x. It tells me right there. Another way of writing x is tangent of u. But that needs to be squared. And now we have the arctangent of u. Well, if I interchange x and u, I get the arctangent of x is u. Oh, okay. Arctan of x is u. This happens to be the same as that. That cancels out. So this time you have the integral of u du. But that's a simple integral. That's u to the 1 du. The integral of u to the 1 du. So that's u squared over 2 plus c. And just type in where u is. That's u. So it's arctangent of x, or tan inverse of x squared, over 2 plus the number c. Okay. Now, I didn't expect that to work out so cleanly, to be honest. What I was going to do is, I'm just going to call the top u. I'm going to call tan inverse of x u. Let u equal tan inverse of x. Well, this part is u. Now this says that x equals tangent of u. So then dx, 1 dx, which is dx, is secant squared of u du. Okay? in, let's see, this was u, and dx is secant squared u du, secant squared u du. Maybe this is not so much different than what we did do. And the bottom, okay. I guess we drew a triangle and we came up with that. Here I came up with it without drawing a triangle. The bottom is 1 plus x squared. But that's how I write x. That's x, and they're squared. These bottom and what I just crossed out are equal. So they divide it out. So you have the integral of u du. Remember, that's u to the 1 du. So it's u squared over 2 plus c. It's u squared over 2 plus c, where u is tan inverse x. Okay? There I did it without even drawing a triangle. Now your teacher's going to tell you whenever you see this, you make that substitution, and here you don't even ever have to draw a triangle. But then you have to remember so much. Suppose you have the integral of x over the square root of 1 minus x squared dx. And suppose the limits are negative 1/2 to 1. I meant to say 0 is probably better. Now, you can do trig substitution here. But you know what? I'm seeing the derivative of that up to a multiple, up to a constant, is that. If I just let u be 1 minus x squared, well then du is negative 2x dx. This bottom, remember, that's u. It's u to the 1/2. And the top, if I sneak in a negative 2 and bring out a negative 1/2, the top is just du. Negative 1/2, the top is just du. And you should rewrite this problem, just bring this to the numerator. But if you go from the bottom to the top, you have to change the sign of the exponent. So it's negative 1/2. The integral of this, well, you add 1 to the power. That is, you add the top and the bottom, and you get 1 over 2. And then you divide by 1 over 2. And 1/2 times 2 cancels. You just get the negative u to the 1/2. Don't bother dividing by 1. And then you substitute back. You get negative. Remember this, you could rewrite that as the square root of u. It's negative the square root of u. But that's u. You want to evaluate this from negative 1/2 to 0. I just hate having a minus in front. I can't do it. It's just too hard for me. I'm not lying. So I interchange those values. Put the 0 on the bottom, the negative 1/2 on the top. When you square negative 1/2, because it tells you to square it, you get a quarter. 1 minus a quarter is 3/4. Minus, when you plug in 0, you get 0 squared. 1 minus 0 is 1. The problem is that doesn't exist. Because that's a negative number. This is negative 1/2. So let's see where, if anywhere, we made a silly mistake. Okay, so I agree with this equal sign and that equal sign. Well, I can't disagree with the first one because we're letting it be that. But if once we let it, du equals negative 2x dx. So this here, if I plug in the -2, that's du, and the bottom is u to the half. Okay, so I have no problem with that equal sign. I have no problem with that equal sign. The -1/2. Okay, I agree with that equal sign. I do agree you get negative the square root of u. What I messed up on was this silliness over here. First, you plug in the upper limit, which is -1/2, minus, not underneath the square root sign, the square root sign ended there, minus what you get when you plug in 0, which is 1. So, you get the square root of 3 over 2, because the square root of 4 is 2, minus 1. There's your answer. You want to write it with the common denominator. Think of 1 as think of 1 as 2 over 2. So you have the square root of 3, take away 2, all over 2. That's your answer, and that happens to be a negative number. There's more of the graph under the x-axis than above. There's more area below the x-axis than above. That's what made it negative. How do I know this is negative? Well, if this number is more than 1, well then when you take away 1, you'll be positive. If it's less than 1 and you take away 1, it's negative. The bottom is 2. The top is less than 2. The square root of 3 is less than the square root of 4, which is 2. The square root of 3 is less than 2. The numerator is smaller than the bottom, which is 2. That means it's less than 1. If you have less than $1 and somehow you go to the bank and you convince them to let you take out $1, well, you owe them money. You're less than 0. This time you owe them. Okay, that finishes that problem. Though I think I wanted to do that problem again. You didn't have enough of it. You can use this trig substitution stuff. I wouldn't, but you could. This is 1 squared minus x squared. Okay, the positive part, namely that's being squared, is plus 1 squared. The 1 goes on the hypotenuse. The minus part that's being squared goes on one of the legs. X is being squared. And the whole square root sign, the whole square root part goes on the other leg. If I call this u, well then opposite over hypotenuse gives me something nice. Not complicated. I can say the cosine of u is 1 minus x squared over 1, but that's too complicated. The sine of u is just x. So differential will be cosine of u du is equal to 1 dx, which is just dx. So the top. Every piece has to be accounted for. Not some, not most, but every. X, well, that's sine of u. Okay, sine of u. Dx, well, oh, that's cosine u du. Cosine u du. And this, well, there's your square root. It's 1 minus x squared. But that's how I write x. 1 minus x squared. However, 1 minus x squared, 1 minus sine squared of u is cosine squared u. And the square root of that is cosine of u. Coincidentally, that cancels out. So we get the integral of sine u du. That integral is negative cosine of u. Okay, but we have a nice triangle. I wrote down the minus sign. We have a nice triangle that will tell me the cosine of u. It's adjacent over hypotenuse. It's just 1 minus x squared. So the final answer is negative 1 minus x squared. And this is going from negative a half to 0. Over here, please. If I multiply this by negative 1, which I'd really like to do, I just interchange the limits. You plug in negative a half, you square it, you get a quarter. 1 minus a quarter is 3/4. So you have the square root of 3 over the square root of 4. Personally, that's how I write the square root of 4. Minus, you plug in 0 for x. 0 squared is 0. 1 minus 0 is 1. Get minus the square root of 1. Personally, that's how I write the square root of 1. And here's the same answer we got before using trig substitution. In case you didn't see that you could get away without using trig substitution, well, we did it with it. Here's a very straightforward one. X over x dx over 1 plus x squared. I would just let u equal 1 plus x squared, and then du will be 2x dx. I kind of have the du on the top once I put in a constant and bring out the reciprocal. This here is du, and as it says right there, that's u. So this is a rather simple integral. And maybe it was hard to make that substitution, but once you did it, it's an easy integral. It's just an integral of du over u, and you're supposed to know that. That's ln of absolute value of u plus a constant. Just substitute back what u happens to be. And don't guess, go and read it off. U is 1 plus x squared. Now, this is a problem. In a textbook, for example, in the back of the book, they most probably would have something like that. And the reason that is, well, what's the difference between these two? And the answer is, we have absolute value bars here, but down here we don't. The reason is we know that x squared is 0 or more. Well, if you add 1, then x squared plus 1 is 1 or more. That means this is positive. It's more than 1 or equal to 1. Fine. It's not less than 0. It's 1 or more, which means it's positive. This means that x squared plus 1 is positive. And the absolute value of a positive thing is just that thing. In this case, 1 plus x squared. You don't need the absolute value bars. If you're in my class and you left your answer like that, you will lose a point because it didn't finish. And let me erase that minus 1 before we think it's one of their limits of integration. Now suppose you have dx over x squared minus 2x plus 2. What we want to do is complete the square on the bottom. Now x squared minus 2x You want to decide, well, you have x squared minus 2x plus 2. So, plus 2. It equals the line below. But what's inside the parentheses, I want it to become something squared. Now, if you have an understood 1 in front of the x squared, and we do, if you take half of that number, if you take half of negative 2, and then you square it, well, half of negative 2 is negative 1. And when you square it, you get 1. If you add that in here, what's inside that parenthesis will be a perfect square. It will be x followed by half of that number. Half of that number. Namely, the number right there. Negative 1 squared. Well, if you add negative 1, you have to take away 1, else it won't equal the line above. You have x squared, you have minus 2x, you have plus 2. Oh, wait a minute, maybe they're not equal. You have other stuff. Oh, don't worry. Plus 1 minus 1 is 0. You can add 0. What's inside the brackets is x minus 1 squared, and positive 2 minus 1 is positive 1. This bottom is the same as x minus 1 squared plus 1, say squared. Now just for the record, if you had x minus 1 squared plus 11, you may say, well, I know what's being squared here. I'm not that bad. X minus 1 is being squared, but nothing is being squared there. That's not true. If you square the square root of 11, you get 11. What's being squared here? Oh, square root of 11. Okay, now we completed the square. Now this looks like one of the earlier problems that we've done. Okay, of course it should say, have an integral sign at the beginning. So now I want to use trig substitution on this. Since everything in the bottom is being squared, that's what goes on the hypotenuse. X minus 1 squared plus 1 squared, the square root. The x minus 1 I'll put here, and since 1 is being squared, I'll put the 1 there, and I'll call that u. Well, the tangent of u gives me the simple stuff, x minus 1 over 1, which is just x minus 1. So that's how I write tangent of u. To get dx, I take the differential. Secant squared of u times du equals the differential of the right-hand side, which is 1 times dx, or dx. Okay, so this top, dx, well, that's easy. That's secant squared u du. And the bottom, well, that's u. Excuse me, that's tangent u squared. So it's tangent u squared plus 1 squared. Oh, that's secant squared u. That kills off the secant squared u in the top, and I just have integral of du, which is u. Well, I give you an integral in terms of x, and you tell me the answer is u. I give you this integral in terms of x, and you tell me the answer is u. I'll look at you rather strangely. You have every right to interchange that. You now know that u, but you have to write tan inverse. You know that u equals tan inverse of x minus 1. So instead of u, I give you back an answer in terms of x. For example, it's some multiple choice test. You're asked to solve this integral, and you have a number of choices. Choice letter A is u squared minus 4. Choice letter B is u squared plus x squared. And choice letter C is the square root of 1 minus x squared. And choice letter D is u take away v. It's not A, because I gave an integral in terms of x's. The answer can't be in terms of u. You may say, well, we made a u substitution. This is not the only u substitution that would have worked. You can make other u substitutions. So if you and I have different values of u, our answer in terms of u will be different. Okay, the answer is not B because it has u's in it. The answer is not D because it has u's and v's in it. The answer, say, would have to be C. Okay, of course, that's also wrong because this is the right answer. But what I'm saying is, this is insane to leave as your answer. Because the person who's looking at just your answer say, oh my, what's u? I mean, you can say this is the answer where u equals this, but then again, that means that. Instead of u, you put this. That's just what we did. If somebody gives you an integral in the letter w, you better give them an answer back using the letter w. Unless it's a definite integral, and you better give them back a number. Okay, here's an interesting problem. Suppose you have the integral of e to the 2x over 1 plus e to the 4x. E to the 2x dx. Now, what you need to realize is that this here is e to the 2x squared. Because when you multiply 2x by 2, you do get 4x. So what I'd probably do is, I would just first let u equal e to the 2x. Well, then du, well, it will be e to the 2x times the derivative of 2x, which is 2, or the differential, which is 2 dx. That is, the top is very close to du. You put a 2 in and you bring out a half. This piece right there, du. And bottom, here's 1 and here's plus, and here's u squared. 1 plus u squared. Now if you do enough of these, you'll learn that that's tan inverse of u. But I'm not into memorizing this stuff. I already used the letter u. So now I'm going to use the letter v. Since everything is understood to be positive, the square root of all that goes on the hypotenuse. One of the things being squared goes here. One of the things being squared goes there. One is being squared. Okay, so this tells me that the tangent of v is u over 1, which is u. Differential. The secant squared of v dv is equal to 1 du. Okay, so we have 1/2. Instead of du, I write secant squared v dv. I write this instead of du. And in the bottom, I write 1 plus u squared. But that's u. U squared. But that's secant squared v, which kills off that one. So we're left with 1/2 the integral of dv, which is 1/2 v plus c. Now we back substitute. This is the same as v over 2 plus c. Well, v is, it's not so obvious what v is. Come in here, we interchange these two, and we get v equals the tan inverse of u. So v over 2 plus c. V is the arctangent of u. The u equals e to the 2x. U equals e to the 2x. U equals e to the 2x. Okay, it's the arctangent of e to the 2x over 2, or a tan inverse of e to the 2x over 2. How you say it, how you write it, that's between you and your teacher, etc. Tan inverse and arctan, they're the same. Suppose you have 2x dx over x squared plus 6x plus 13. The first thing I would do is I factor out the 2. Now, the derivative of x is not 1 over x squared plus 6x plus 13. The derivative of the bottom is not the top. Okay, so what we're going to do here is we're going to complete the square on the bottom. The 2 is factored out, the top is x dx, and the bottom is going to be something squared plus or minus some number. X squared plus 6x plus 13. We want to add something inside here. And then we're going to take it away. We're going to add on half of that squared. Half for 6 is 3. And we're going to square that. We're going to square this 3. We're going to get a 9. So if we add 9 here, I have to take away 9 there. Now what's inside those brackets is a perfect square. It's x followed by half of that number, which is right here. It's understood to be plus 3 squared, and plus 13 minus 9 happens to be plus 4. So that's the bottom. X plus 3 squared plus 4. Trig substitution problem. Let's get rid of most of this. So sometimes you have to complete the square before you can really even start the problem. Since both things are understood to be plus, all of it goes on the hypotenuse. X plus 3 squared plus 4 with a square root. The x plus 3 goes here, and the 4 is understood to be 2 squared. The 2 goes there. Call that angle u. The sine of u, opposite over adjacent, is something very nice. The sine of u is x plus 3 over 2. Sometimes I like to bring the 2 up there, but we'll leave it this time. Cosine of u du is 1/2 dx. Okay, well, if we put the 1/2 in front and bring out the reciprocal, that's allowed. So what's in front is 2 times 2, which is 4. The whole numerator, 1/2 x dx. Oops. What is going on here? Okay, I take that back. Let's just, okay, we didn't do anything wrong other than saying the whole numerator was dx. Just put the half closer. That's du. Okay. So that's du. On the bottom, if I think of the 2 being up here, this is 2 sine u squared, which is 4 sine squared u. Don't forget plus 4. Everything in red I dealt with. I haven't dealt with that x yet. Let us solve this for x. Let's just take away 3. If I take away 3 from the left side, I get x. Well, I have to take away 3 from the right side. So we get x times du. We have 2 sine u minus 3 times du. That's where we're at. And just so I don't lose it, the substitution we made was 2 sine u is x plus 3. Okay, so let's erase a lot of this stuff and let us see what we can do from here. Okay, now in the bottom, I can factor out a 4. Yeah, 4 times 2 sine u minus 3 times du. I can factor out a 4 from the bottom, and I'll be left with sine squared u plus 1, because I factored 4 out from there as well. To save a little space, well, first 4 over 4 cancels. Save a little space, you have to remember that sine squared u plus 1 is cosine squared u. This is cosine squared u. This little x on the top is causing us an awful lot of problems. Okay. I guess there are other ways of doing this. So now, let's continue. It's the integral. Since it's a subtraction, it's 2 integrals. It's the integral of 2 sine u over cosine squared u du minus the integral of 3 over 3 du over cosine squared u. Okay. We are making progress. This 2 I'll bring out in front. But on the side over here, let's look at sine u over cosine squared u. Well, that's sine u over cosine u times 1 over the second cosine u. This here is tangent u. That's tangent u. And 1 over cosine u is secant u. Okay, so that's just how I'm going to write that. We have 2 times the integral of this times du. So what I circle is really tangent u, secant u times du minus the 3 I'll bring out in the front. The du is in the top, but the cosine squared in the bottom is the same, cosine squared of u in the bottom is the same as secant squared u in the top. Okay, now we're almost done. The integral of this is what? That's the integral of secant of u. Minus 3 times the integral of secant squared u is tangent u. I know so, because the derivative of tangent is secant squared u. The derivative of secant u is secant u tangent u, or tangent u secant u. Okay, now all I have to do is substitute back what u is. In fact, let's just look at the triangle over here. Secant of u, well, secant is hypotenuse over adjacent. Okay, so it's 2, that 2 times the square root of x plus 3 squared plus 4 divided by the adjacent, which is 2, minus 3 times the tangent of u. Well, tangent of u is opposite over adjacent. Opposite is x plus 3, the adjacent is 2. If you want, you can write everything with a 2 in the bottom. So the top will be this minus that. 2 times the square root of x plus 3 squared plus 4 minus 3 times x plus 3, before I forget, plus c. Plus c. Plus c. Okay, there's your answer. Long problem, have to be able to do it. I'm not very good at these. If I can do them, so can you. Okay, let's try this one. Suppose you have dx over x take away 1 times x squared minus 2x, all under the square root sign. What you could do, since I see x times x minus 1, is you can let u equal x minus 1. If u equal x minus 1, then add 1 to both sides, you get x is u plus 1. This will be u, that would be u under the square root, and that would be u plus 1, and dx would just be du. But let's not do that just yet. I want to complete the square underneath that square root sign. You have x squared minus 2x. What do you add? Half of that number squared. Half of negative 2 is negative 1. And that's what we squared to get 1. So that's what I'm going to add. That here is a perfect square. But I added 1 out of nowhere. Have to take it away. What's inside those big brackets is x followed by that number. Squared minus 1. Actually square that out. Make sure that you are getting x squared minus 2x plus 1. Okay, so what we have is dx over x minus 1 square root of x minus 1 squared minus 1. Now, if you wanted to let u equal x minus 1, you can do that. You wouldn't be done. You'd have to do what we're doing next. The only thing is instead of having x minus 1 to deal with, you would just have the letter u. But x minus 1 is not all that complicated. We'll make a u substitution. Trig substitution. The understood positive part, that goes on the hypotenuse. The part that's after the minus that's being squared, namely 1, that goes here. And how about we put it here? And over here we put the whole square root. X minus 1 squared minus 1. Okay. Well, this time, you know, I'd rather reverse it. Just let that equal 1. The bottom leg is 1. Okay. So this tells me that I'm going to do this divided by 1. That gives me a very friendly answer. Hypotenuse over adjacent, that's secant. The secant of u is x minus 1. Differential of both sides, secant of u, tangent of u, du equals differential of that, which is dx. Okay, so the numerator is secant of u times the tangent of u times du. X minus 1, well, x minus 1 is secant of u, okay? Secant of u times the square root. This here is secant of u squared minus 1. Well, let's look at this. If you have sine squared u plus cosine squared u equals 1, and you divide both sides by cosine squared, let's write that down again, please. Sine squared u plus cosine squared u is 1. If we now divide both sides by cosine squared u, cosine squared u, cosine squared u, same thing over here, I ran out of space, that will be tangent squared u plus, that of course is 1, and 1 over cosine squared u. 1 over cosine squared u is secant squared u. That is, if I bring the 1 to the other side, we have secant squared u, take away 1 is tangent squared u. That is, this here is tangent squared of u. But the square root of tangent squared u is tangent u, which kills off that tangent u on the top. Secant u over secant u gets killed off. So we just have the integral of du. Let me finish this on the very, very top right, please. The integral of du is u plus c. Now we just have to write u in terms of x plus c. Now, we know this statement right here. Well, I could interchange those. I can say the secant of x minus 1 is u. Excuse me. But then I have to say inverse. Secant inverse of x minus 1. Okay, that's just what I'm going to write. The secant inverse of x minus 1. That's your answer. The secant inverse of x minus 1 plus a constant. Okay, that finishes up the section on what I call trig integrals, or trig substitutions. Most times they involve inverse trig functions, but not each and every time. And most times they will. Okay, good luck with them. Thank you.